Alrighty, so it is 5 minutes after the top of the hour. Once again, thank you everybody for joining us today. My name is Nagam Matu. So before starting this town hall, I'd like to give a shout out to Paul Carlson and Roxanne McKay from Maryland Transportation Authority for connecting us with our speakers today. Just to give you a little bit of context behind the reason of holding this town hall. So a few months ago, as most of you know, FHWA released their notice of proposed amendment for the manual and uniform traffic control devices, or as all of you know it as the MUTCD. And one of the proposed provisions, which was in particular in part 5, included a specific provision that stated that electronic traffic control devices such as traffic signal heads and digital signs are kind of like required to have a flicker rate of at least 200 hertz. So the IEEE P2020 group is actually working on this particular issue, and we are so fortunate today to have both Brian and Robin to present to us and share their expertise and findings regarding this topic. So with this being said, I'd like to introduce Brian Deegan from Valeo Vision Systems and Dr. Robin Jenkin from NVIDIA. They are both active members of the IEEE P2020 group, with Brian being the chair of the flicker rate subgroup. So once again, Brian and Robin have kindly agreed to share the group's findings and discuss the rationale behind this proposal. Well, basically behind the finding of the rationale behind the 200 hertz, not necessarily the proposal. And the purpose of this town hall, which is really important, I would like to stress it out, is really to know what does our members, the industry, partners as well, how do they feel about this, and if we can take steps moving forward to actually bring everybody to the table, you know, along with manufacturers, vendors, and everybody, and stakeholders and key players to discuss this furthermore and continue the conversation. One small housekeeping item: we will be using the Q&A feature. My teammate Pamela and I will be monitoring these, and feel free to just ask your questions throughout the presentation. With this, I will turn it over to Brian.
Thanks, Nagam, for the introduction. Can everyone hear me? Is my voice coming through? Very good. Okay, so I'll just start sharing my screen. Now the second hurdle. Am I sharing my screen? See my slide deck?
Yes.
Looks perfect, Brian.
Okay, okay. Very good. 2 for 2. Excellent. I'll just give it a second. It's still loading. Still loading. There we go. So again, thanks again for the kind introduction. So good morning, good afternoon, and good evening to everyone on the line, depending on where you are in the world. As Nagam said in our introduction, I'll just be giving a brief introduction into LED Flicker, which is the topic of today. Its root cause and impact, particularly for, I suppose, the automotive camera industry and its impact on things like autonomous driving. And I'll just give a quick introduction to the IEEE P2020 working group, the kind of topics that we're working on, and I suppose the scope and names of the working group. So just to move quickly on to the P2020 working group. So the P2020, IEEE P2020 working group was founded a number of years ago now by, I suppose, a number of key players within the automotive camera industry. I suppose OEMs, tier 1s, tier 2s, test houses. We basically all got together, and there's kind of a general realization that in terms of I suppose automotive camera image quality, that a lot of the existing standards that are out there for assessing the quality of a camera were not fit for purpose for modern automotive cameras. So there's a number of existing standards, for example, but a lot of them are based on, I suppose, consumer cameras for cell phones and DSLRs and stuff like that. but they were not fit for purpose for camera systems on vehicles, particularly for things like assessing quality of cameras with very high, very wide field of view lenses. I mean, some of our cameras go up to 200 degrees field of view, so they're literally seeing behind themselves. And there's also other challenges relating to high dynamic range imaging, which I'll come to in a minute. And I suppose just generally the challenges of making sure that you have a camera that will work well in all conditions and that will be suitable for supporting the function of autonomous driving and things like that. So with that, we got together and formed P2020 working group. We're hoping to have our initial draft standard maybe later this year, and there's already white paper up online if you're interested there, and the link will be shared below. Yeah, so and I suppose just give as I mentioned before, in terms of the background, the scope of I suppose camera image quality, it covers everything, as I said, from scene viewing applications. So this is things like backup cameras and stuff like that that augment the driver's field of view around the vehicle, all the way up to machine vision applications which support autonomous driving. And I suppose the challenge of LED Flicker itself, that actually applies to both. It's important consideration for both viewing and for machine vision applications, as I will get into later on. I suppose in terms of the number of cameras and the type of cameras that are in modern autonomous vehicles, you have everything on the left will be what would be called the near field cocoon. So that would typically involve very wide field of view cameras that see the immediate area surrounding the vehicle. So this is for things like driver assist, like simple backup cameras, to surround view viewing cameras, and even for things like autonomous parking. This is usually for this usually applies to kind of these kind of wide field of view cameras, basically to protect you from things within a couple of meters of the vehicle. And then in the kind of the more autonomous driving kind of field, there will be kind of this far field cocoon, which would involve some narrow field of view cameras. These would be for seeing down the highway, like 50 to 100, 200 meters down the highway. And then there's also wider field of view cameras closer to the vehicle for detecting things like traffic lights, road signs, things of that nature, and I suppose crossing vehicles, things closer to the vehicle. Okay, so back to the P2020 working group. Within the group, there's currently 4 active groups. One is a kind of a cross-functional group, which is defining, I suppose, cross-functional requirements and specifications across all 3 of the other working groups. There's subgroup 1, which I'm the chair of, which is looking at LED Flicker standards. There's also another group that's working on image quality for viewing, and Robin, in addition to being the secretary of P2020, is also leading those efforts. And finally, there's image quality for computer vision standards. So target, as I said, for publication is in 2021. I suppose within the scope of P2020 and the work that that MISO group is working on, the main goals are to basically describe the theoretical background of LED Flicker, to capture use cases and potential risks, to identify other image quality factors which must be considered when assessing LED Flicker, because there are a number of different factors when it comes to camera image quality that need to be considered, and to define recommended test methodology and objective metrics for assessing LED Flicker at the camera level. And I suppose this is I suppose a point that I want to highlight up front as well, in terms of the scope of what we're working on for P2020. We were founded, and our aim is primarily on techniques, methodology, and metrics for assessing camera image quality. Our main scope is not to define recommendations for I suppose for lighting in the automotive environment. And when I say lighting, I kind of mean everything from traffic signals to vehicle lighting, street lighting, all that kind of thing. Our scope is, like I said, it's primarily about camera image quality assessment. It is not within our direct scope to provide recommendations to lighting bodies, But as was mentioned earlier, we do have a lot of experience in this area. We've gathered up a lot of use cases, and I suppose we think it's good to kind of share, I suppose, a lot of the knowledge that we've gathered. So I suppose we can ultimately, I suppose, engage with the working groups such as yourselves, I suppose, to make the broader automotive community aware of the I suppose the challenges and impacts of things like Flicker. And this is a picture of the working group. This was the last time we all got together before the pandemic struck, and hopefully it won't be too long before we can start taking pictures like this again. Okay, so that is the background to the P2020 working group. Now, over the next couple of slides, I'll go into more depth on LED Flicker itself, what causes it, the use cases where it's a problem, and the impact within those use cases. So, LED lighting. So, I suppose one of the main reasons why this is becoming more and more of a problem for the automotive camera industry is because the widespread use of LED lights within the automotive environment. So you can see everything from electronic road signs, vehicle lighting, traffic lights, everything like this is migrating away from more traditional light sources to LEDs. And there's many good reasons why this move is happening, from cost, power consumption, reliability, design flexibility. All these kind of things are significant advantages for, I suppose, pulse width modulated LED light sources. As I mentioned as well, LEDs, they're typically driven by what's called a pulse width modulated signal. So the LEDs, in order to modulate brightness, quite often you don't adjust the power or the current directly applied to the LED. Instead, you use like a pulse width modulated signal. So instead of the light being constantly on, it is toggling on and off at a very high frequency, at a frequency which is beyond the range of human vision to perceive, but does basically affect the camera. And I suppose the reason why PWM is used is it gives a better brightness control, it reduces power consumption, and it's better for color constancy. So there's many good reasons for doing it. The brightness itself as well, which I'll go into more detail later, the output brightness of the LED is basically a function of the frequency of the PWM signal, the duty cycle, is basically the relative on versus off period that the light is on, and the applied current. And I suppose one of the critical points here as well is that once the frequency of the LED that is being powered by, once it's greater than 90 hertz, typically then it appears constant to a human observer. Yeah, and I'll just give a quick background into digital cameras as well. Just I suppose for the audience here as well. So I won't go into too much detail on it, but a camera is basically that we're using. Fundamentally, it's the main components are the lens and the image sensor as well. And then after that, you have like an image signal processor, which processes the raw image from the sensor and converts it to either into a color image for viewing or into some other type of image that will be used by machine vision functions to support things like autonomous driving. In terms of how the brightness of the image is controlled, it's controlled by a number of key things. At the lens, the main parameter is what's known as the F number of the lens, and that to kind of simplify it, it basically represents how much light the lens allows onto the image sensor. Then after that, at the sensor, the brightness is controlled by the exposure time, so how long you expose the pixel to light for, the gain that you apply, and then I suppose post-processing. Now, for many kind of consumer cameras, you would have a lot of flexibility in terms of how you manage your brightness control, but in automotive cameras, there's typically less flexibility. One of the main reasons for this is that the F number is fixed, so you don't have a variable aperture. So that reduces a lot of the flexibility. And I suppose managing brightness control in automotive applications is very important as well. So for example, if you want to be able to image a traffic light, the exposure control of the algorithm, it needs to prevent the image from becoming too bright, because if the image is too bright, for example, you won't be able to see the color of the traffic light. Conversely, if the image is too dark, you need to increase your exposure time so that you can see things in the shadow. So for example, if you want to detect a pedestrian in a shadow at nighttime, you need to have a long exposure so you can gather enough light in order to be able to see someone in the dark. One of the challenges in automotive is quite often you need to be able to see both at the same time. So you need a long exposure time to see details in the shadow, and you need a short exposure time to capture bright details. So if you imagine a scene where you're trying to detect with the same camera, like a traffic light, to be able to detect the color, and also pedestrian that might be in a shadow at the same time. So that's usually beyond the capability of normal cameras that have used in consumer electronics. So in order to do that, automotive cameras usually have to be high dynamic range cameras. Usually that involves taking multiple images, multiple input images, and kind of stacking them in order to generate what's known as a high dynamic range image. So you might have, for example, 3 different captures, one for the shadows, one for the midtones, one for the highlights, and you merge them together in order to form your final output image. Yeah. So now onto the problem of flicker itself. I'm going to try and play this video. I'm very conscious that this is over WebEx and over Zoom and stuff like that, so this may not play very well, but I'll try and play it anyway. What you'll see here is that these running lights in the vehicle here are blinking on and off. So this is one manifestation of the problem that we're talking about with LED flicker. So I'll show still images of it later, but what's basically happening here is when these lights are being driven by LED lights are being driven by PWM signals, sometimes they blink on and off. So this comes back to our definition and our problem statement. LED flicker is basically an imaging artifact whereby a light source or a region within a captured image or video sequence appears to flicker, even though the light source will appear constant to the human observer. It usually manifests as either a light source blinking on or off. It can also be a modulation in brightness and or color of the light source, or a banding artifact, and I'll show an example of that later, similar to what you see if from an alternating current light source. And there's 2 basic categories. There's one category where the flickering light source is in the field of view of the camera, and that's probably more relevant for this particular audience. So things like traffic lights, temporary road signs, and vehicle lights and things like that. And there's another class of problems when an LED light source is being used to illuminate the scene. Why is this important? Well, depending on the use case, the impact of a flicker can range from being a mild annoyance, serious distraction on one end, but at the higher end, it can potentially negatively impact functions which are trying to support autonomous driving. So in terms of the use case, yes, it can have potentially very serious consequences for the camera systems that are trying to image the environment. And the other point as well is that it's to prevent it or to mitigate it is technically very challenging and introduces its own side effects quite often as well. And this last statement here, that there's no standard test methodologies for quantifying this, hopefully by the end of the year that statement will no longer be true, and we'll have our first draft published. Okay, so in terms of some of the use cases that we go through, so not quite as relevant for this audience, but one use case that we have is, and again, this mightn't come through very well over WebEx, but what's happening in this scene is this is a camera mounted in the dash, looking at a wall at nighttime, and this light here is this is the reflection from the headlights on the vehicle itself. So you can see here that we have this very noticeable on-off pattern being reflected, and if you play the video through and if you can see it in real time, it's actually really distracting. It's and is potentially distracting for a driver that's attempting to use the system. This is one of my favorite use cases. This is for a mirror replacement system. So this is a camera that replaces the typical in-cabin camera. So what I want to draw your attention to is this light blinking on and off here. Just that's just following the mouse. What's interesting about that one is that looks like a turn signal. So looking at it, it appears as though that the person driving this car wants to change lane. But that's not actually what's happening in this case. What's happening in this case is this is actually flickered. This light there's also an LED over here, which just happens to be off all the way until the last second. And this one just happens to be blinking at the exact same frequency as a turn signal. So you can see, for example, like for vehicles that are trying to, camera systems that are trying to tell if a vehicle wants to change lanes or merge or something like that, that's problematic. And I've also heard of use cases in this particular application where people saw LED flicker that looked a bit like this, and they thought it was an emergency vehicle, like an unmarked police car or something like that, and they actually changed lanes to make way for the emergency vehicle. So that's obviously problematic as well from a safety point of view. Yeah, this is an example like that of that use case. It probably won't come across too well, but you can see the lights are blinking on and off, and that looks quite a bit like the lights that you'd see from an emergency vehicle. And probably the most relevant use case for this audience for traffic light detection. So this is a video that was captured in Japan. So you can see here the traffic light blinking on and off quite a bit, and you can also see there's kind of a color shift that's happening as well. So this red light is starting to look more like a yellow traffic light as well. Yeah, the video won't stop. Okay, there we go. Okay, let's see what's going on here. Okay, sorry, now I'll just go back a second. Okay. Yeah. So as you can see here, this is a still frame taken from that video sequence. So you can see here in this example, if you're trying to detect the traffic light from this image, you can see that all three of the traffic lights appear off. So that's clearly a challenge. Another use case is for things like temporary speed signs and stuff, or electronic speed signs. You can see here in this particular example, it appears off. Again, another example here caused by LED flicker, where this temporary road sign is not readable, and things like highway signs as well when they're LED driven as well. So again, if you've an autonomous vehicle application that's trying to read these signs, obviously that's a challenge. Yeah, and there's a zoomed in version. Okay, so to summarize, what causes LED flicker? It's basically a combination of LEDs being driven by a pulse width modulated signal. Usually it happens when you have LEDs running at a relatively low frequency with relatively low duty cycle, so that the light source is off quite often. That combined with, I suppose, scene conditions and their impact on the camera system, and I'll go into more detail on that later, can create this effect. Like I said before, the main standard that's out there right now, the only one that we can find really that goes into any detail on this is for European temporary speed sign standard. And that basically says that greater than 90 hertz is required, so that it appears constant for human vision. However, when it's imaged by a camera at lower frequencies like this, then you're more susceptible to get LED flicker. So what's actually going on when this is happening? So if we go back to this video that I shared earlier, so you can see in this frame, just the still image taken from the video sequence, you can see the lights are off, and then in the next frame the light appears on. So same traffic light, on versus off. So if we break it down, what's represented here is we have our traffic light, and these are the adjacent frames. This line here represents the LED signal that's driving, or the PWM signal that's driving the LED, and this is the exposure time of the camera. So for a digital camera, it's not capturing light for all of the frame period. It's actually the exposure time is usually significantly shorter than the frame period. And when I say frame period, for example, if you're capturing at 30 frames per second, which would be standard for video, then your frame period would be like 1/30, which would be 33 milliseconds. So basically every 33 milliseconds, you're capturing a new image, but your exposure time is usually shorter than that. Going through this now, so if we look at this particular example for this particular video frame period, we can see here that our exposure time at the camera, which is aligned to the end of the frame, it coincides in time with the LED pulse. So you can see here, while we're exposing, we capture the LED pulse, so the light appears on. In the next frame, however, just because of the relative timing between and the relative phase between the camera exposure time and the LED pulse, in this case, the exposure time is happening when the LED pulse is off. It misses the LED pulse, so in this case, the light appears off. And this is how you end up with the light blinking on or off. It's all down to the phase between your exposure time and the light, and obviously the shorter the exposure time and the shorter the duty cycle and the lower the frequency of the LED pulse, the more likely this kind of effect is to happen. Other effects that can have when these kind of LED lights are illuminating the scene, we can also get these banding effects. So you can see here in this particular example, we have a light band and a dark band. And what's going on in this particular use case as well, it's similar to the first one. Usually this happens in a darker scene. In the first frame, which would represent the lighter band in the previous image, we can see here the exposure time is longer and we capture 2 pulses of the light. So we capture the light with a certain intensity. And then in the next frame, just because of the relative phase between the two, we only capture 1 pulse. So because we only capture 1 pulse, the intensity of the light that's captured by the camera is less. So it's captured with a different brightness level. And then as you go frame by frame by frame, the brightness level modulates. It goes up and down depending on how much light is captured, which is determined by the phase that we're seeing here. Another thing to be aware of as well for cameras, most cameras that are used in automotive tend to be rolling shutter as well. So that's one of the things that contributes to the banding effect that we're seeing here as well. Now this is particularly relevant for things like street lighting and stuff like that. If that's illuminating the scene, we'll end up seeing those kind of banding effects a lot more that I showed earlier. And I suppose the frequency and the width of the bands, or the height of the bands rather, I should say, is basically a function of the I suppose the beat frequency between the camera frame rate, the rate at which the camera is capturing new images, and the frequency of the PWM light source as well. So you can see here, for example, as we sweep through 100 hertz to 1000 hertz, at around 100 hertz, we have relatively low frequency bands, whereas at higher frequencies, we get these higher frequency bands. And what I mean by that is there's more light and dark bands within the image. And you can actually calculate in advance what your beat frequency is going to be. So it's basically going to be, it's going to be kind of the modulus of the of your camera frame rate and the frequency of the light source. So you can see here, for example, at 60 hertz, and if we're assuming a 60 frames per second frame rate at the camera, then at 60 hertz, and then again at a multiple of that at 120 hertz, we have a 0 hertz beat frequency. So what that means is, in the previous example for those bands, the bands will be static within the image. And then as you get more, as the frequency drifts between up to 90 hertz and then back down to 120 hertz, the beat frequency increases. So in this case, the lines would sweep through the image much faster before slowing down again once you get to the multiple of the frame rate. So both of these at both extremes are actually problematic. If your frequency is the same as your frame rate, or if it's an integer multiple, then, for example, depending on the relative phase between your exposure time and the light in the scene and stuff like that, if you're trying to image a traffic light, for example, it could appear off indefinitely if you end up in exactly the wrong phase lock kind of situation. And then if you're somewhere right in between the two, like here, you can end up with very fast modulation. And if someone's viewing that, if an observer is looking at a signal that's modulating at 30 hertz, it's pretty uncomfortable. It's not pleasant to look at. Okay. There's other challenges that are applicable for automotive camera systems. As I said before, the dynamic range is usually high dynamic range is usually required for autonomous cameras. This is because let me see this slide. Usually you have a big difference in brightness between things that you want to capture in the scene. So usually you want to be able to see things in both shadows and highlight at the same time, and that's usually beyond the capability of cameras to detect. So the way around that, traditionally would be to do things like multiple exposures to capture the shadows, midtones, and highlights in the scene at the same time. And that's usually done by taking pictures with 3 different exposure times. When it comes to LED flicker, that can cause a very specific artifact, which you can see here in this example. In this particular use case, these buses, the lights here were driven by a flickering signal, and you can see here, this is one frame, and this is a later frame within the same video. And what's actually happened here is the color information is completely missing in this example. It's supposed to be a yellow light, but it's there's no color in this particular example. And this is caused by a specific I suppose manifestation within multi-capture HDR schemes. So what's happening here, for example, similar to the previous diagrams, if you have, for example, let's say you have a use case where you have 2 exposures being used to extend the dynamic range, what can happen here is for T1, for the longer exposure time, you capture the pulse that very bright, so you get a very bright image capture. But then for your second exposure, which happens in sequence in time, you completely miss the pulse, in which case you end up with a completely dark image. And then when you go to merge something that's very bright and overexposed with something that's completely underexposed, you end up with this, when you average the 2 of them together, basically, you end up with a kind of a flat gray that actually has no signal content in it. And this is an example here taken from a lab condition. So you can see here multiple exposures were taken. In the long and medium exposure, the light source is completely overexposed, it's completely white. And then in the underexposed image, it's in the short exposure, it's completely underexposed. You go to merge the 2 together and you end up with this gray artifact here. So for example, things like traffic light detection, when you're trying to detect the colors, that's obviously a problem. So to summarize the root cause analysis of this, LED flicker occurs when the exposure time of the camera is less than 1 over the PWM frequency of the light being captured. There's also the secondary effect related to HDR image sensors, which I just covered. This causes combination artifacts, in which case you can lose signal to noise, and you can lose color. In other scenarios, typically in low light conditions, the number of pulses can vary from frame to frame, and this can cause modulation in terms of brightness and color, and it can also cause the banding artifacts, which I showed earlier. Okay, I'm conscious of time here, so I'll keep moving reasonably quickly. I just want to go through a couple of quick points, so I'll skip. Okay, I'll just verbally go through this. So this problem of LED flicker, it's not necessarily new. It's been a problem that's been getting steadily worse, but it's been a problem for camera systems for a couple of years now. In terms of mitigating it at the camera level, it's not necessarily straightforward. in order to mitigate it, basically what you want to do is you want to have a longer exposure time at your camera so that you can be guaranteed to capture at least one pulse of the LED light. This is not possible in a standard pixel design, because the image will overexpose on a bright day and then you end up with no information. So the challenge for that is you need to be able to increase your exposure time of your camera, but without having the pixel overexposed and saturated and basically go to pure white. So all the major sensor vendors who work within the automotive industry have been working on this challenge for a couple of years, but it requires, I suppose, a very specific sensor design, which does come with its own trade-offs. Largely in, so obviously the ideal case, you'd want no degradation in cost, dynamic range, signal to noise, color accuracy, frame rate, and motion blur artifacts. Typically for mitigating flicker, you typically pay a penalty in practically all of these different considerations. And I suppose at a I suppose it's not something that you can I suppose get out of by post processing either. So what some people have done in the past to try and mitigate this problem has been to kind of take multiple images, average them together to kind of average out the modulation. But as we saw in some examples, sometimes you can miss the light pulse for tens of frames, in which case it's not really feasible to do this, because it's not safe and it's not really possible to buffer enough frames in order to do that. I suppose in terms of buffering or I suppose getting back to the sensor discussion, if you want to increase your exposure time long enough to be able to capture at least one of these pulses, a simple challenge with that is if you increase your exposure time in order to do that and you successfully mitigate flicker, you still have a longer exposure time. And one of the problems in that in automotive is things move through the scene, or the vehicle itself can be moving. And by increasing your exposure time, you're starting to introduce things like motion blur. So for example, if you're trying to detect a traffic light at any kind of a velocity, if you're increasing your motion blur because you need a longer exposure time, obviously that's a challenge as well. So I suppose to summarize it though, I mean, the image sensor vendors and the automotive camera industry is moving towards mitigating the problem, but all of these mitigation steps, they do come with trade-offs in terms of cost, complexity, and introducing other image artifacts. So, so I suppose to summarize, I've already said that. In terms of recommendations, from a camera side of things, like I mentioned, LED flicker can be mitigated, but it cannot be solved completely. This, for simple reason, is like there's no standards out there in terms of the frequencies, duty cycles, etc., that can be used. So the camera, it's not like there's a standard that all camera systems could configure their settings to in order to mitigate this problem. Or to eliminate the problem. It can be mitigated by making sure you never miss a pulse, but that comes with its own trade-offs. In terms of working with the with the lighting community, and if we had recommendations that we would make, and again I want to stress, these are kind of these recommendations are more in the context of starting a discussion rather than IEEE coming in and mandating standards for lighting, because that's not within our scope or within our mandate. Generally though, what I would say is using higher frequencies is generally better. Higher frequency, the worst case scenario is low frequency, low duty cycle, because that's in that combination the light is off for the longest. So the higher the frequency and the higher the duty cycle, the less of an issue that you would have. It's when choosing frequencies, above 200 hertz is better. The higher the better would be even better, because that would allow us to use a kind of a shorter exposure time and prevent things like motion blur and overexposure. Avoiding things like well, I suppose more strictly for vehicles and stuff, to avoid frequencies that would end up with a beat frequency around 2 hertz, because then lights can look like turn signals when they're not. Higher beat frequencies in the range of 15 to 20 hertz are also ideally they should be avoided as well, because if you have a human observer looking at these kind of high beat frequencies, they're very visually disturbing. That's it. So again, I'd like to thank you for your attention. As I said, this the main purpose of this is, I suppose, is to introduce the problem and to kick off the discussion. And if there's any follow-up questions, you can either contact myself or Robin, who's on the line here as well from NVIDIA, and our details are there. Oh, thank you very much.
Thank you very much, Brian. That was really eye-opening. I remember the first time I sat through your I sat through your presentation, I was just mind blown that this is even a thing. And I'm like, no, I have to see it. So I was walking around with my phone, taking videos of traffic signals and digital signal signs, and I was mind blown. I'm like, oh my God, it is a challenge, and I can't imagine how more challenges there will be, you know, because I also hear that the technology when it comes to cameras and automated vehicles, it keeps like progressing and changing. So I would also expect that would introduce, you know, further challenges. And thank you very much for making this presentation. And I really hope that we will be taking this, you know, we will continue this conversation and be proactive to kind of find a solution that would meet everybody's kind of needs and to improve safety. I do have a few questions here, so I'll start with the first one that we got. It was from Steve Oros. It mentions, has this group researching LED Flicker reviewed the proposed update to the MUTCD in the US?
Yes, so as you'd mentioned, like the NCUTCD, I've already presented, and you would have seen that slide deck there. So yes, we're in discussion with them. The proposal is to go to 200 hertz. That would be a good start, I suppose, from the camera industry side of things, because it would allow us, so we avoid things like overexposure in scenes, we avoid things like motion blur. So that would definitely be a good start, I suppose. With I would even prefer to see it go higher, but that's there's once you start to go higher, significantly higher than that, I suppose there's some trade-offs and things that would need to be discussed. I think from talking to that group as well, I think there were some concerns about require significant financial investment, and it would take time in order to introduce a standard like this. So within the automotive, I suppose we're fully aware of that, and we know that this is not something that would happen quickly. This is something that would have to be phased in and would take quite a while to come through. But at least, I suppose, if we start having this kind of discussion, I think that's at least the right step forward.
Awesome. We have another question. I think that it relates to the metrics and the numbers. It relates to the question, to some of the answers that you provided right now. It says we have a question current during PWM 1/10 duty cycle at 1 kilohertz to 10 kilohertz. Does this introduce a challenge for the camera?
1 kilohertz to 10 kilohertz. It depends on how that's used, I suppose, is a short answer. So if it's a straightforward PWM that's running at 1 kilohertz, that's it still causes a challenge. But again, once you get up to frequencies that are that high, it becomes less of an issue. It's really only when you have frequencies that are, I suppose, in the kind of the lower hundreds that it's a bigger problem. But I suppose the other challenge as well is that sometimes high frequency pulses, you can use a load of small pulses in order to generate a kind of a slower, kind of a square wave. So if it's if you're using a high frequency in order to kind of generate a kind of a low frequency curve, then again we're back to having a problematic condition then. So I suppose it. I'm going to see if I can draw this. So
Brian, maybe I can add some.
Yeah, if you have a pulse like that, it's fine. Yeah, Robin, I'll let you go in 2 seconds. Yeah, but if you have like a train of pulses that looks like this, if you have like a stack of pulses, where is it? There we go. if we have a high frequency load of with a load of high frequency pulses, again, something like that can cause a problem.
All I was going to add, Brian, is that so if you have the 1 kilohertz, and 1/1 kilohertz is still like 1 millisecond, and that's still the gap between that, the one. So for HDR systems, we could have like 1 microsecond or 2 microsecond exposures, and it still ends up being a little bit of a problem when you have very, very bright lights that appear in, say, T3 or T4, when you've got these 1 microsecond exposures. So, you know, personally, I'd like to see duty cycles that are increased beyond 10%, ideally, and that's with my NVIDIA hat on. Yeah.
I suppose, yeah, that's a point worth emphasizing as well. Both of us are here kind of with 2 different hats on. We have like the IEEE hat, in which case, you know, we're limited in what we can say because the scope of what we're doing is, I suppose, about camera standards. But we also have our day jobs in which we're looking at this. And so when Robin says he's talking with his NVIDIA hat on, he's talking about, I suppose, very real challenges that he's seeing. So yeah, so Robin, you're absolutely right. Like, I mean, again, the higher the frequency, the better. The longer the duty cycle, the better. 1 kilohertz is better than what's currently out there, but you're right, it still will cause challenges, particularly on bright days and with bright light sources that you're trying to image.
Got it. We have another question from Seth Chalmers. It says, are there any issues with LED street lighting?
The short answer is yes. These, like I said before, when you have LED street lighting, you have 2 problems. One is the LED itself. If that's visible within the field of view of the camera, that'll flicker, but it'll also cause wider areas to flicker as well. So that's where you start to see those kind of banding effects that I showed earlier. In terms of the, and maybe Robin, you can correct me on this, I've seen less examples of LED streetlights causing problems. I think generally right now, they're not driven in such a way that they're probably more DC than PWM, so I don't think it's as common. But in principle, the same problem would apply.
Yeah, the only thing I would add to that is that because of the mains phase, then we're usually locked into 11 millisecond or 8 millisecond long exposures. And that can sometimes be restricting when you're trying to set up a sensor. So one thing Brian maybe didn't mention is that the development of these systems on the cars is very much more like development for aircraft rather than development for the consumer industry. We have a very significant safety case to answer to when we develop software and systems for this, and so we tried to avoid a lot of automated processing or automated changes in the camera to try to make the safety case as simple as possible and as robust as possible. So the exposures that we set have a lot of constraints on them, like the global mains flicker, and then some of the higher frequency flicker as well. And so the global mains flicker really limits or constrains the longer exposures that we can use to avoid the banding that Brian is talking about. So if I had one desire for say mains-based street lighting, whether it's incandescent or LED-based, it would be to try and put something in there that would get rid of the 50 or the 60 hertz flicker completely, you know, a little circuit there. But it's more a constraint than a hard problem, because at the moment we solve it by locking the long exposures to multiples of 8-ish or 11-ish, 10-ish milliseconds.
Awesome, thank you. We have another question here from Stéphane Lapierre. He's asking, if I understand the recommendation for DMS manufacturer is to set the PWM backclock to 600 hertz.
Yeah, that was one of the things that we looked at, and again, this isn't a hard recommendation at all. This is just one of the possibilities, but this speaks to the point that that Robin mentioned earlier. So one of the reasons 600 hertz was mentioned is because it is a common multiple of 50 and 60 hertz. So depending on where you are in the world, you're either in a 50 hertz regime or 60 hertz, and so if you're at 600 hertz, you could kind of double up and kind of, I suppose, deal with a lot of the street lighting and the LEDs at the same time. So that was the rationale behind that one.
Awesome.